Good day! I will be discussing some sample problems to illustrate the calculations involved in the flotation process. Calculations for flotation processes generally have two types: designing and evaluating a current design. Design problems involve calculating for the required dimensions of the flotation unit to impart a certain level of efficiency given the feed and product characteristics, whereas the second type is concerned with the amounts and concentrations of the feed, product, and intermediate streams given the design and specification of the equipment. Sample problem number 1. Compute the required length L for a flotation cell with a depth 4 feet and a width 2 feet if it is fed with pulp having the following characteristics: volumetric flow rate 100 gallons per minute, concentration 1% volume per volume, density of water 1000 kilograms per cubic meter, viscosity 1 centipoise, specific gravity of solution 1, and specific gravity of oil 0.87. Recall that in deriving the equations to be used in solving these types of problems, certain assumptions were made. Hence, before employing the said equations, we must first check their validity in our particular problem. Assumption 1. Solution is dilute and settling is unhindered. These were assumed in the start of derivation for the rising velocity so that the interactions between the particles are negligible and the only forces acting on the particles are weight, buoyant force, and drag force. Assumption number 2. Aggregate particles are spherical in geometry. In assuming this, the expression for drag force was simplified. Assumption number 3. All the aggregate particles have the same density. Since particles extracted through flotation are usually denser than water, reagents that take advantage of the wettability and hydrophobicity of the components of the pulp, together with the air bubbled into the cell, induce a decrease of effective density to the aggregate particles. It was assumed that this decrease imparted by the treatment is constant among all the particles. Assumption number 4. The vertical motion of the particles are independent of their horizontal movement. The first assumption is applicable in this problem since the solid concentration, 1% volume per volume, is considered sufficiently dilute. With the second assumption, we can use the given particle size interchangeably with particle diameter. For the third assumption, only the density of oil is given in the problem. Oil was used as the reagent. The white dots are the particles which, due to their hydrophobic nature, cling to the oil droplets, the blue circles. Considering that the particles have negligible mass and volume compared to the oil droplets, the aggregate density approaches the density of oil. The fourth assumption can only be satisfied if the flow of the stream is in the laminar regime, since during turbulent flow, there are bulk movements within the fluid. These bulk movements can occur in planes perpendicular to the horizontal, hence may affect the rising velocity of the particles. Also, the drag force in turbulent flow is quite difficult to obtain because the chart used to determine the drag coefficient is plotted on logarithmic axis. Therefore, we need to check if the flow is laminar using the criterion K, where K is equal to the diameter of the particle multiplied by the cube root of the product of the gravitational constant, density of fluid, difference of density of the particle in the fluid, over the square of the viscosity of the fluid. Notice that instead of an exact value, a range of particle size is given. How do we determine which to use in the equations? The smallest particles impart the slowest movement throughout the unit, and so they give the largest tank length. Use the smallest diameter for all equations requiring dP. Computing for K, we obtain a value of 1.0844, which is less than 3.3. The flow is therefore laminar. By multiplying the horizontal velocity by the time required for the particle to float, we get the distance the particle moved along the horizontal before it reached the top of the cell. The distance computed is also equal to the minimum length needed to be able to collect the smallest particles of interest. The horizontal velocity can be obtained by dividing the volumetric flow rate of the stream by the cross-sectional area of the cell. Time required for the particle to rise is simply the depth divided by the rising velocity. The rising velocity is derived to be equal to dP squared g quantity raw minus raw p all over 18 mu. After calculating these intermediate values, the length of the tank is computed to be 48.006. Sample problem number 2. It is desired to recover lead from a 100-pound ore being treated for 24-hour day, containing 10% lead sulfide and the balance assumed to be silica. It is assumed that the concentrate from a single cell is of acceptable purity, but the tailings are to be treated in scavenger cells with return of scavenger concentrate to the rougher. Laboratory findings indicate that if the water to solids ratio L over S is equal to 2, and the contact time is 8 minutes in the rougher, and L over S is equal to 4 for 15 minutes in the scavenger, with mechanically agitated machines for the Denver type, the following compositions will be found for the various products. First, calculate the volume of lead sulfide and saline. Then, compute the average density of every stream using the given mass fractions and densities. Create an overall mass balance, A is equal to B plus E, and a lead sulfide balance around the whole system, XA times A is equal to XB times B plus XE times C. Since A is given to be 100 pounds and the mass fractions are all known, we can calculate B and E by solving the two equations simultaneously. B is equal to 11.9 pounds and E is 88.1 pounds. Considering the scavenger tank, the mass balance is C is equal to D plus E. The lead sulfide balance, XC times C, is equal to XD times D plus XE times E. With two equations and two unknowns, we can compute for C, which is equal to 102.67 pounds, and D, which is equal to 14.57 pounds. The product yield is equal to the mass fraction of desired in the concentrate multiplied by the mass flow rate of the concentrate all over the mass fraction of desired in the feed multiplied by the mass flow rate of the feed times 100%. In our case, the desired component is lead sulfide. Substituting, percent yield is equal to 95.2%. To compute the tank volumes, we must first identify which streams are temporarily stored or treated in each tank. For the rougher tank, the streams are A and D. Calculating the average density of the mixture, rho AD is equal to 176.8. Then we must compute the volume fraction of solids, which is simply the volume of the solid over the volume of the solid plus the volume of the fluid, usually just water. The volume of water can be determined by multiplying the water-solid ratio L over S by the mass flow rate of the fluid divided by the density of water. The volume fraction of solid is then equal to 0.1492. The capacity can be estimated by dividing the product of the volume fraction of solid and average density by the residence time. Converting the units, we get 2.378. Similarly, for the scavenger tank, average density is equal to 167.3. Volume fraction of solid is 0.0851 and capacity is 0.682 tons solid per cubic feet per day. And that is the end of the sample calculations. Thank you for listening.
Everything's better with Harry. Everything's better with Harry. Everything is better with Harry. Everything's better with Harry. Everything's better, and we just wanna tell you, Harry. Everything's better with you.